The ignition system plays a crucial role in engine performance. In this module, we'll take a look at how a capacitor discharge, or CD, ignition system operates. Understanding how the system works is essential to effective troubleshooting. The capacitor discharge, or CD, ignition system provides up to 50,000 volts and a quick spark that reaches its peak voltage in 3/millionths of a second. This helps fire even wet, worn, or carbon-fouled spark plugs. Another important benefit of CD ignition systems is that each ignition coil is located very close to its spark plug. This eliminates wasteful high-tension distribution systems and minimizes secondary voltage loss. To understand how CD ignition systems operate, let's take a close look at a 3-cylinder outboard ignition system. A CD ignition system includes 2 sets of magnets. One set is on the hub, and the other is on the outer rim of the flywheel. Sensor coils and charge coils are located under the flywheel. The power pack is a mysterious black box to most people, but you will understand it before the end of this module. Ignition coils are located close to the cylinder heads and spark plugs. Let's examine all of the components in the system, beginning with the charge coil. When the first pole of a flywheel magnet passes the charge coil, current in the coil flows in one direction. When the second pole of the magnet passes the charge coil, current flows in the opposite direction. This process, repeated every time a flywheel magnet passes the charge coil, results in a continuous output of alternating current, or AC, from the charge coil. The capacitor, located in the power pack, is a device that stores electrical energy for use at a later time. You can think of the capacitor as a spring-loaded chamber full of electrical energy under your control. When you decide the time is right, you can release all of the energy stored in the capacitor. The capacitor needs direct current, or DC, to work properly. Direct current flows in only one direction. To convert AC flowing from the charge coil to DC for the capacitor, we use a device called a rectifier. The rectifier, located in the power pack, uses a bridge of diodes that act like one-way valves for electricity. No matter which way the electricity flows into the rectifier, it comes out flowing in one direction. Notice that one wire from the rectifier goes to the capacitor, and the other wire to the engine block. Metal in the engine block serves as a ground, a common return for current flow. This symbol is used in circuit schematics to indicate engine ground. Because electricity can only travel in a complete circuit, the aluminum engine block supplies a convenient path for current to return to the rectifier and capacitor, and eliminates the need to run wires between all of the system components. Before we continue, let's summarize how the charge coil and rectifier work together to charge the capacitor. Rotating flywheel magnets generate approximately 300 volts of alternating current in the charge coil. AC flows from the charge coil to the rectifier, where it is converted into direct current. Approximately 300 volts DC flows from the rectifier to the capacitor, where it is stored for later use. Each cylinder has its own sensor coil and silicon-controlled rectifier, or SCR. These two components work together with the sensor magnet to ensure each cylinder's spark plug fires at the correct time. The sensor magnet, located in the hub of the flywheel, induces approximately 3 volts in each sensor coil every time its poles pass by. 3 sensor coils, one for each cylinder, are precisely positioned under the flywheel. Each cylinder's sensor coil sends a signal to its SCR. SCRs, located in the power pack, are like tiny electric switches. Together with the sensor magnet and sensor coils, SCRs control the discharge of voltage stored in the capacitor to the ignition coils. An SCR has 3 wires. One connects it to the capacitor, one connects it to the ignition coil, and one connects its gate to the sensor coil. The gate controls the SCR. When sensor coil voltage is applied to the gate, current flows from the capacitor through the SCR to the ignition coil. When the capacitor discharges all of its energy, the switch opens and the capacitor begins recharging. Let's review how the sensor magnet, sensor coils, SCRs, capacitor, and ignition coils work together to fire the cylinders. Each sensor coil is positioned under the flywheel to fire a specific cylinder. When the sensor magnet passes sensor coil number 1, current flows to SCR number 1. SCR number 1 discharges the voltage stored in the capacitor to ignition coil number 1, which fires spark plug number 1. Because the ignition coil and capacitor are both grounded to the engine, the circuit is complete. The remaining two cylinders fire the same way. When the rotating sensor magnet passes sensor coils number 2 and number 3, their SCRs trigger their respective spark plugs to fire. How can only 300 volts DC, applied to an ignition coil, fire a spark plug? 300 volts isn't enough to jump across the gap of a spark plug. The answer is that the ignition coil is a transformer. It can transform electricity from one voltage to another. Inside the ignition coil are loops of wire, called windings, wrapped around a ferrite core. There are two sets of windings, the primary windings and the secondary windings. As the capacitor discharges, current flows through the primary windings, inducing a magnetic field around both windings. As the capacitor's stored energy quickly dissipates, the magnetic field surrounding the windings collapses, generating voltage in the secondary windings. The voltage you get out of an ignition coil depends on how many volts you put into it, and the ratio between the number of windings on the primary side and the secondary side. Because the ignition coil has only a few primary windings and many secondary windings, it steps up or increases the amount of output voltage. An input voltage of 300 volts DC applied to the primary windings generates an output voltage of approximately 50,000 volts DC in the secondary windings. Because an ignition coil can only transform potential energy, not create it, amperage from the coil decreases as its output voltage increases. This isn't a problem because only a modest amount of current is needed to fire the spark plug. 50,000 volts DC is more than enough voltage to jump across the spark plug's gap and ignite the fuel-air mixture in the cylinder. Now that we have our engine running, how do we stop it? All we have to do is connect a wire from the rectifier to a switch grounded to the engine block. Now, when we close the switch, current from the rectifier takes the path of least resistance and flows to the engine block instead of the capacitor. The switch also shorts out the capacitor by connecting both ends of the capacitor together, effectively releasing any charge that might be stored in the capacitor. It's really double protection. With no rectifier current reaching the capacitor and the capacitor shorted out, current cannot reach the spark plugs, and the engine stops running. But there is one other question we need to answer. Engines require different timing of the spark at different speeds. At high RPM, the spark must occur earlier in the combustion cycle. How does the ignition system accomplish this? The sensor coils are located in a movable assembly called a timer base. Linkage connects the timer base to the throttle control. As the throttle is advanced, the timer base moves counterclockwise. The flywheel rotates clockwise, so moving the timer base counterclockwise causes the spark to occur earlier, or advance. CD ignition systems used on 2, 4, 6, and 8-cylinder outboards operate much like the system we've just examined. Of course, with more cylinders, you need more SCRs. V6 models have 2 charge coils under the flywheel and 2 capacitors in the power pack, one set for each bank of cylinders. Today's power packs include additional features. For example, when an engine exceeds its rated speed, the power pack causes the engine to misfire by shorting out some of the spark impulses. This feature limits engine RPM and protects it from damage. Many outboards include features like Quick Start and Slow. Quick Start advances the spark timing of an outboard so it runs at a fast idle until it warms up. Quick Start advances spark timing when the engine is operating below approximately 1100 RPM. A temperature switch located on the cylinder head grounds out at a preset temperature, signaling the power pack when the engine is warmed up. Idle timing cannot be verified when the ignition is in the Quick Start mode. If the timing jumps back and forth between 2 readings, the engine is probably in the Quick Start mode. The Slow feature, speed limiting operational warning, gradually limits engine RPM if the outboard overheats, protecting it from damage. A temperature switch located on the cylinder head signals the power pack to limit engine RPM by creating a connection to ground when the engine reaches a preset temperature. On outboards with optical ignition, an optical sensor replaces the sensor coils and magnets. Power for the optical sensor comes from the power coil located on the stator assembly. An ignition analyzer is used to test optical ignition systems. The analyzer verifies the optical sensor is working and allows both idle and maximum timing to be adjusted without running the engine. The procedures for troubleshooting and repairing CD ignition systems are fairly simple and straightforward. You check the condition of individual components and replace those that don't meet service manual specifications. An ohm meter is used to check the resistance of the charge coil, sensor windings, and ignition coils, and to verify that none of the components have shorted to ground. A peak reading voltmeter is used to check the voltage output of the sensor coils, charge coil, and power pack. When troubleshooting and performing repair procedures, always be sure you are using the correct service manual for the year and model engine you are servicing. These procedures are not general in nature and change from year to year. You can destroy a good component simply by following the wrong testing procedure. Outboard ignition systems have come a long way since Ole Evinrude marketed his first outboard in 1909. Today's CD ignition systems help provide boaters with smoother running, more durable, and more reliable engines. By understanding how CD ignition systems work and how to properly troubleshoot and repair them, you will keep your customers satisfied.